This is your presenter Asloob Mudassar, and I am presenting slide number 107 of the course on laser physics. Question is, in connection with the electric pumping, discuss number 1, thermal and drift velocities, number 2, electron energy distribution, number 3, ionization balance equation, number 4, scaling laws for electrical discharge lasers, number 5, pump rate and pump efficiency. So we have to discuss these 5 points in our discussion. The answer is first we are going to discuss the first point, which is the thermal and drift velocities. In the process of gas discharge creation, electrons acquire energy from applied voltage and then lose or exchange their energies involving the following 3 processes. Number 1 process is there will be more frequent electron-electron collisions provided the gas ionization has occurred to an appropriate level. Due to like particles, energy exchange will be high and the repulsive forces will be exerted from large distances. The average energy of the electrons stays the same. Collision process will only redistribute the electron energies. So I think that this is quite clear. Point 2 is, in the elastic collision process, the atoms are relatively at rest and change direction randomly after collision with an average loss of energy of the order of 2 times m over capital M, where small m and capital M are the masses of the electron and atoms respectively. So you see that here we are assuming that the atoms are initially at rest. So the velocity of the electrons initially is 0. And after the impact, the atoms will gain some energy. We may assume here that the electrons is bounced back with probably the same amount of energy. So using the conservation of momentum, we can find out this relationship, that is the ratios of the velocities is proportional to 2 times of m over capital M. And similarly, we can also obtain this relation from the difference of kinetic energies, that is the initial kinetic energy, that is the kinetic energy before collision minus the kinetic energy after collision. That will give you, that will be equal to the energy loss, and that energy loss can be computed to be equal to 2 times m over capital M. Here we are not interested in giving you the detailed description of this quantity, but here just take it as granted. The elastic collisions are more frequent than inelastic collisions. Elastic collisions do not contribute in the pumping process and will reduce the efficiency of the pumping process. This will result in heating up the gas rather than exciting the gas atoms or molecules. So you see that in the elastic collision, you know that there will be a very small amount of exchange of energy. And when there is a very small amount of exchange of energy, it means that the electrons are not capable of exciting the atom or to ionizing the atoms. So only elastic collisions will contribute in the collision process, heating up the gas, because the system is not perfectly isolated. So the energy is not perfectly conserved. So there is a loss of energy in the process of heating up the gas molecules. So elastic collisions is not contributing in the process of pumping. You know that the pumping process requires the excitation to the required levels. That is the excitation to the from the ground level to the required excited level, which corresponds to the upper state level of the lasing process. And in the elastic collision, no such things happen. So we can say that the contribution of the elastic collisions during the in the pumping process is almost 0. The third point is inelastic collision. In the inelastic collision, the gas atoms are either raised to the excited states or ionized, depending upon their energy. The inelastic collisions play the most important role in the electric pumping process, because this is the process that will impart a huge amount of energy from the, that is the electrons will impart a huge amount of energy during the collision process to the atoms. So electrons in a discharge have distribution of velocities. So these electrons are not monoenergetic but have a distribution of velocities. Let the distribution be assigned by the function f, which is a function of Vx, Vy and Vz, where Vx, Vy and Vz are the components of the electron velocity along the x direction, y direction and z direction respectively. And f function will give you the distribution of these velocities or the energies of the electrons. The probability that the electrons have velocities in the range from Vx plus minus dVx, from Vy to Vy plus minus dVy, and from Vz plus minus dVz. So this is given by, we multiply the distribution function, which is f of Vx, Vy, Vz, with the incremental variation in velocities, which is dVx, dVy and dVz. So if we multiply, that is, we have f of x, f of Vx, Vy, Vz multiplied by dVx, dVy and dVz. This amount will give you, this will give you the probabilities that the energies of the electrons will lie in the interval of dVx and dVy and dVz. Electrons' thermal velocity, denoted by V thermal, is defined as the square of V thermal is equal to the average of V square, where V square is the kinetic energy of the electrons. So average of square of the velocities will give you the square of the V thermal. And this average, which we have taken around the velocity of the electrons, this average is calculated over the velocity distribution. So V thermal square is averaged. So V thermal square is calculated from the average of V square, which is, and the averaging process is done using the velocity distribution. And the V drift is defined by V drift, which is the drift velocity of the electrons against the applied electric field, which is equal to average value of Vz, whereas Vz is the z component of the velocity, and we have taken the average of all the electrons which are present there. So that will give you the overall velocity, overall drift velocity of the electrons, which will tell you that whether the electrons are moving or static. If the electrons are moving, they will move opposite to the direction of the applied electric field. Where Vz is the z component of velocity taken in the field direction. The average kinetic energy of the electrons is half mv thermal square. So you see that here we have used the average kinetic energy. So we have averaged the kinetic energy of all the electrons present in the discharge tube, and we are talking about now the average kinetic energy, which is equal to half mv thermal square. Now let's define V thermal over L as the average collision rate. You see that the dimensions of this quantity is 1 over time. So that's why V thermal over L is regarded as the average collision rate, where small l is the electron's mean free path. That is the path that the electron will travel between two collisions, between two consecutive collisions. So the average power lost by the electron will be equal to its kinetic energy, its average kinetic energy is equal to half mv thermal square multiplied by the average collision rate, which is V thermal over L, and multiplied by the by delta, which will represent the loss of power during a collision. So the average power lost by the electron is given by equation number 3, where delta is a constant fraction of the kinetic energy lost by the electron in a collision process. So you see that in each collision, of course, the electron, the kinetic energy of the electron will be lost, and delta will care of that fraction because it provides you the fraction with which the energy is lost. This power loss is balanced by the power supplied by the electric field. You know that the electric field is represented by E times zeta, where zeta is the applied voltage. Multiplying it with E will give you the electric field. So E times zeta is the electric field, and if you multiply electric field with the V drift velocity, V drift, you will get the power. So the force multiplied by velocity is the power. So the upper power which is lost, we have mentioned over here, that is the average power lost by the electrons. This will be compensated or balanced by the power supplied by the electric field, which is the power, and the power is equal to E times zeta times V drift. So we can equate this on the left hand side of equation number 3, and we get this result as shown in equation number 4. That is E times zeta multiplied by V drift is equal to delta times of V thermal over L multiplied by half mV thermal square. Let's consider the electron's journey during a mean free path. Let V thermal is the velocity of the electron at the start of the mean free path, that is just after a collision. So you see that we are starting the electron's journey. We are considering the electron's journey after it has just encountered a collision, and just after the collision it starts its journey, making an angle with the field direction. At the end of the journey, that is after covering a distance L, that is just before a second collision, the electron's velocity is given by. So during one mean free path, the velocity change will be v prime. So v prime will be equal to v thermal plus v drift, because the electron is subject to two types of velocities. One is the v thermal velocities, which is the average velocities of the electrons with which the electrons are moving in the sample. And then of course the V drift velocity, and V drift is also the velocity of all the averaged velocities of the electrons moving under the influence of the electric field. That is the whole sample of the electrons either moving towards the electric field opposite to the direction of the electric field. So V prime will be equal to V thermal plus V drift, where V drift is the velocity acquired by the electrons opposite to the field direction during the distance L. Now we want to calculate the change in momentum. You see that in the change in momentum, we have to find out this is the initial momentum, this is the final momentum, mv prime. That is the momentum just before the second collision. So mv prime is the final momentum minus mv thermal is the initial momentum. That is, this is the momentum, mv thermal is the momentum with which the electron started its journey, and after covering a distance L equal to the mean free path in the presence of the electric field, its momentum was m times v prime. So m times v prime minus mv thermal is the change in momentum. Now we are going to replace v prime from this relationship from equation number 5, and we have substituted the value of v prime over here, which is equal to v thermal plus v drift, and then we have minus m times v thermal. So you see that m times v thermal shown in red will be cancelled by m v thermal shown in blue, and then we are left with m v drift. So the change in momentum during this journey will be equal to m times v drift, as shown in equation number 6. This change in momentum is due to the applied field and can be equated to. So you see that in the previous we have converted using the electric field, we have converted that one into the power. For example, this is the applied field, zeta is the applied voltage, E zeta is the electric field multiplied by the V drift velocity will give you the power supplied by the electric field. Now we want to, using the electric field, we want to calculate the momentum, because this change in momentum is due to the applied electric field. So E minus E times zeta is the electric field multiplied by L over V thermal, because L over V thermal has the dimensions of time. So electric field multiplied by time, that is the force multiplied by time, will give you the change in momentum, and this change in momentum has caused the change shown in equation number 6. So equating these two results will give you minus E times zeta times L over V thermal is equal to M times V drift. So rearranging this equation in the form of equation number 7, we have a minus E times zeta times L is equal to M times V thermal times V drift. So you see that now we have V thermal and V drift present in equation number 7. You can see on the right hand side we have the V thermal and V drift present on the right hand side in equation number 7, and similarly we have equation number 4. You see that in equation number 4, V drift is present on the left hand side and V thermal is present in two form, in the linear form and in the quadratic form on the right hand side in equation number 4. So we can solve these equations and we can find out V thermal, which is equal to 2 divided by delta raised to the power 1 over 4 times E times zeta times L divided by M whole fraction raised to the power half. So this is the value of V thermal given in equation number 8. Similarly, V drift is given by V drift is equal to delta by 2 whole fraction raised to power 1 over 4 and multiplied by E times zeta times L divided by M whole fraction raised to power half. So we have obtained V expression of V thermal shown in equation number 8, and we have found the expression of V drift shown in equation number 9. Now let's compute the ratio of these two velocities, which is given in equation number 10. So V drift divided by V thermal is equal to delta divided by 2 whole raised to power half. We can identify delta as the fractional loss of kinetic energy during an elastic collision, where delta was equal to 2 times of m over capital M. And you see that we can use capital M, that is the mass of the atom, to be nearly equal to 10 to the power 4 times in mass of the electron for those gases which are generally used as lasing materials. So substituting this ratio to be equal to 10 to the power minus 4 and then substituting over here in the form of delta, or in this equation number 4, in equation number 10, you will see that we get V drift over V thermal to be equal to 10 to the power minus 2. So it means that V drift is a small fraction of the V thermal. Thus, the randomly moving electrons in a gas discharge are slowly drifting opposite to the field direction as a whole. So this point is very important, which we have established, that the V thermal velocity is very large, 2 orders of a magnitude larger than the V drift velocities. Thus we can, on the basis of this, we can say that the randomly moving electrons in a gas discharge are slowly drifting opposite to the field direction as a whole. The appearance of delta in equation number 4, with delta as a fractional loss of kinetic energy during a collision, is not perfectly correct for inelastic collisions, where the loss in kinetic energy may be significant, appearing as the excitation or the ionization of the colliding particles. But you see that even under this caution, that is delta will not be an appropriate value, is not an appropriate fraction when in the case of an inelastic collision, because the energy transfer will be huge in the form of excitation of the atom or in the form of ionization of the atom. But still the results are useful and we can still use these results in our calculations. Or at least we can get an idea that the V drift velocity, that is the electrons are very slowly drifting in the towards the opposite to the applied electric field, whereas the V thermal velocities are 2 orders of a magnitude greater than the V drift velocities. So the next is the electron energy distribution. Electron energy distribution. In a gas discharge, if the electrons redistribute themselves very quickly, so you see that this word is important, very quickly, under electron-electron collision, the distribution can be predicted by Maxwell's Boltzmann function. So F of E, that is this will give you the distribution of electron energies. So F of E is equal to 2 divided by square root of pi multiplied by with the KTE, and then multiplied by E over KTE whole raised to power half, then multiplied by E to the power minus E over KTE, where TE is the electron temperature. And you know that TE, which is the electron temperature, is a measure of the average kinetic energy of electrons in a system. And F of E multiplied by dE is the elemental probability that the electron's kinetic energy lies between E and E plus dE. And you know that the kinetic energy is defined, kinetic energy of single electron is given by E is equal to half mv square. Solving it for v square, we get v square is equal to 2e over m. The thermal velocity is computed from V thermal square. You know that we have already given this expression that V thermal square is equal to average of V square, and the average of V square is defined by the integral, that is which contains V square multiplied by F of E, that is the probability function, and then dE. So we can solve this integral because both things are available. That is, we have the expression for V square, which is V square is equal to 2e over m, and also we have the expression for F of E, which is the Maxwell's-Boltzmann function, giving you the distribution of energies of electrons. So you see that if we plug in these two values in the integral, that is in this integral, and solve the integral, we shall get V thermal is equal to the square root of 3 kTe over m. So this is the expression for the V thermal. That is the thermal velocity of the electrons is given by this expression shown in equation number 12. But thermal velocity is also given by equation number 8, which we reproduce over here. That is V thermal is equal to 2 over delta whole fraction raised to power 1 over 4, and then E into zeta over L divided is E into zeta into L divided by M whole fraction raised to power half. So equating the last two expressions, we for V thermal we get and solving the resulting equation for the value of electron temperature, we have TE is equal to 2 over delta raised to power half, and then E over 3 kT multiplied by zeta into L. So this is the expression of the electron temperature. Obviously, from this equation 13, it is obvious that TE is proportional to zeta times L. But you know that L, which is the mean free path, is inversely proportional to the pressure, where P is the gas pressure. This implies that TE is proportional to zeta over P. A detailed treatment of the subject reveals that the electron temperature TE is in fact a function of zeta over P. That is, TE can be written as a function of zeta over P, as shown in equation number 14. According to Maxwell-Boltzmann distribution, the velocity distribution should be isotropic in space, which means that the electron's drift velocity should be zero, which implies that no current will flow through the discharge. But V drift is a small fraction of V thermal. This is what we have proved earlier. We thus consider that the electron distribution is not affected by V drift. Thus, electrons distribution may be considered as Maxwell's Boltzmann distribution. If the gas is weakly ionized with high electron impact cross-section, then due to low electron concentration, the redistribution due to electron-electron collision will be slow. You know that this collision, which is the electron-electron collision, is very helpful in obtaining a redistribution of electrons. But if we have a gas which is very weakly ionized, then of course the electron-electron collision will be very rare. And if there are some electron-electron collisions, then the process will be very slow. That is, the process will very slowly redistribute the electrons or the energies of the electrons or the distribution of the electrons compared to inelastic collision. where the inelastic coquillions will be dominant, and inelastic coquillion will then be helpful to redistribute the distribution of electrons. This condition also supports the validity of Maxwell-Boltzmann distribution. You know that when inelastic coquillions occurs, what happens is that dips may be observed in the energy distribution function at the energy locations, which corresponds to the inelastic coquillion or the transitions. So when inelastic coquillions will occur, then of course a lot of energy transfers to the atom, and then of course the electron distribution. If you measure the energy distribution of the electrons, you will notice a dips in there, because a lot of energy is missing from the distribution at the location of the coquillions. The coquillion may result in the excitation or in the transition or in the ionization of the atoms. Ionization balance equation. Electrons and ions pairs are produced during the discharge process in a gas, which must counterbalanced by the electron-ion recombination process. This is referred to as the ionization balance, and the equation governing this process is regarded as the ionization balance equation. This situation arises under the steady state condition. Electron-ion recombination could be radiative and non-radiative. In the non-radiative recombination process, the colliding electron and the ion are not subject to conservation of total momentum and total kinetic energy. For simplicity, we consider head-on collision. The conservation of momentum and energy give the following equations. For example, the conservation of momentum gives m1v1 plus m2v2 is equal to m1 plus m2 times v, and the kinetic energy moment conservation of kinetic energy gives half m1v1 square plus half m2v2 square is equal to half into m1 plus m2 multiplied by v square plus er, where m1 and m2 are the masses of the electron and ion respectively, and v1 and v2 are their corresponding velocities before collision. V is their combined velocity after the recombination process. Any value of V cannot satisfy both equations. The radiative electron recombination satisfies both momentum and energy conservation in the presence of a third partner represented by capital M, the tube wall. When the low pressure gas is contained in a cylindrical tube with Vm as the velocity of the third partner after collision, the two equations would then contain two unknowns V and Vm. The recombination process at the wall would require the electrons and the ions to reach the wall at the same rate. A fast approaching electron under a radial field would be slowed down, whereas a fast approaching ion would speed up and approach the wall with relatively same speed. So you see that here we are talking about the movement of electrons and ions under the influence of the radial field, not the axial field. Here we are talking about the radial field. A fast approaching electron under a radial field will be slowed down, whereas a slowly approaching ion would speed up and approach the wall with relatively same speed. The gas pressure P and the tube radius capital R are the key parameters. If ions means free path, if ions mean free path represented by Li, I stands for ion, is shorter than R, that is Li is less than capital R, electrons and ions both reach the valve under the diffusion process, which we call ambipolar diffusion, and the recombination occurs. But if Li is of the order of R, or slightly greater than that one, electrons and ions both reach the valve by free flight and consequently recombine. The balance equation according to the Schottky is given by average value of V times sigma I multiplied by Ng is equal to KTE over E multiplied by mu plus and then multiplied by the square of 2.405 divided by capital R. Where sigma I is a function of capital E, that is the energy of the electrons. So sigma I is a function of E is the ionization cross section. Mu plus is the ion mobility, and the average value of sigma I depends on the value of T. Here mu I, which is the ion mobility describes how fast an ion moves through a gas under the influence of electric field. Ionization is produced by the most energetic electrons, and the number again depends on the value of Te. For the ground state population, Ng is proportional to the pressure, and sigma I, which is the ionization, and sigma I, which is the ionization cross section, depends inversely upon the value of pressure. So equation number 17 can be expressed as, with the rearrangement of term, equation number 17 will look like as shown over here. That is average value of sigma into average value of V into sigma I divided by KTE is equal to mu plus divided by Ng into E multiplied by the square of 2.405 divided by R. Both left hand side and right hand side can be written as the function of Te, that is the function of electron temperature. For example, the right hand side can be written as for the right hand side we can write f of Te is equal to capital C divided by the square of PR. You know that R square is present over here in the denominator, so we have R square, and Ng, you know that is a function of pressure, and the mobility of ions is inversely proportional to pressure. So we have P square in the denominator, and similarly, and we have R square in the denominator, already very evident. So we have F of Te is equal to capital C over square of PR, and C is some constant. And the left hand side is also a function of T, which we can write explicitly as F of Te is equal to average value of V into sigma I divided by KTE. So we have written function of electron and function of electron temperature in two different expressions shown in equation number 18a and 18b respectively. Capital C is a constant. Equation number 107.18, that is the equation number 18, including both 18a and 18b, is the ionization balance equation, which relates Te with PR. In the same way as the momentum balance equation relates Te with zeta over P. So the relation, this one, that is F of Te is equal to capital C over PR square, that is the square of PR in the denominator, is actually the ionization balance equation, and which relates Te, electron temperature, with PR in the same way as the momentum balance equation. Te and zeta over P are related. Scaling laws for electrical discharge lasers. Scaling laws for electrical discharge lasers are actually based on the following two equations. First equation is electron temperature Te is a function of F of zeta over P, making equation number 19, and equation number 20 is F of Te, that is the the function of electron temperature is equal to constant over square of PR. That is, in the denominator we have a P square and R square. Assume that a gas discharge exists in a tube of radius R0 and that its pressure is adjusted in order to produce a stable glow discharge. That is, for R is equal to R0, we set P is equal to P0. These two, R is equal to R0 and P is equal to P0, ensure stable glow discharge. The fixed values of R is equal to R0 and P is equal to P0 will fix TE value as obvious from equation number 20. So if you have in equation number 20, if you have R is equal to R0 and P is equal to P0, it means that you have also fixed the value of TE. The fixed value of TE in equation number 19 fixes zeta over P, or equivalently fixes zeta over P0, which means that zeta gets fixed. So you see that as equation number 20 fixes the value of TE, it means that on the left hand side the TE is fixed, and on the we have also fixed the value of P is equal to P0. It means that zeta, the value of zeta, which is the applied voltage, is also fixed. Thus, a stable glow condition would require a fixed value of zeta, irrespective of the current flowing through the tube. This explains the curve in figure number 105.2 around the operating region C, where the desired voltage is independent of the change in current around the operating point C. So this figure has been discussed in question number 105 or in slide number 105, and I am reproducing it using the appendix. For example, over here you can see that this is the VI characteristic curve of a gas discharge and of a DC voltage, DC supply voltage shown in dotted line. For a detailed description, you should consult slide number 105. But you see that when the value of RB is very high, you are just at the start of this solid curve. When you start lowering the value of RB, then the ratio Vp over RB starts increasing. That is, the current I through the discharge starts increasing, and you see that this curve goes up. That is, the voltage across the electrodes starts increasing, and then you know that after the peak value Vp, there is a fall in voltage. It means that now when the fall occurs, then it means that the glow has occurred, has produced in the gas. So this is the region of glow discharge, and B is the point where the discharge is unstable, and then further lowering the value of RB will further increase the value of current through the discharge, and then you see that ultimately we reach the point C. C is the point which is the operating point, and you see that the value of C will give you the desired voltage represented by VDES, desired voltage, and this desired voltage is constant, and you see that it stays constant for a significant value of the variation in the current of the glow discharge. Okay, so you see that this is what I have explained over here. Let me repeat some sentences. This explains that the curve in figure number 105.2 around the operating region C, where the desired voltage is independent of the change in current around the operating point C. We have just seen that R and P for a given gas fixes the value of TE, which we call as a TE is equal to T opt. OPT stands for optimized value. Optimized value for the optimized pumping, for optimized pump rate. If TE is very low, the electrons will not have sufficient energy to excite the gas to the desired upper laser level. The electron's energy will then be used up in the elastic collision and in exciting gas particles to the levels below the upper laser level. On the other hand, if TE is much higher, the electrons will excite the levels above the desired upper laser level, and the excitation energy will be wasted if the excited levels are not coupled with the upper laser level, or the electrons will produce excessive ionization, which will lead to unstable discharge resulting in an arc. So for T is equal to T opt, the optimized and unoptimized quantities from equation number, the optimized and unoptimized quantities from equation number 19 and 20 are respectively related to the following equations. That is, zeta over P can be represented in terms of the optimized quantities equal to zeta over P opt, and similarly for equation number 22 we can have PR is equal to PR opt. That is, on the right hand side we have the optimized quantities, that is R is equal to R naught, P is equal to P naught. These are the optimized quantities. So these two equations give the scaling laws for any gas lasers. So you see that for any gas laser, we have to use these two equations in order to obtain the stable glow discharge. Let's demonstrate the use of these equations. Assume that a gas laser is operating under optimum conditions, and that for some reason its tube radius is to be reduced by a factor of say 2. To keep the system in optimized condition, the gas pressure must be doubled, as shown as follows from equation number 22. So you see that if you make the value of R to be equal to half, that is, you replace R by a value of R by 2, then you need to make pressure P is equal to replace P by its double value, that is, replace P by 2P, so that you will have the same value at the optimized conditions. Okay, when P becomes doubled, then from equation number 20 to 21, it follows that zeta should be made doubled also. This means that the voltage across the laser tube will also be doubled. The VI characteristic curve in figure number 105.2 will scale up by a factor of 2. That is, you see that this one will be scaled up by a factor of 2. So this curve will extend upward by a factor of 2. So you can extend this curve by upward by a factor of 2. Because we have made the value of radius of the tube by half value, we need to double the pressure, and when the pressure is doubled, then of course we need to have the double the value of the applied voltage, and then of course we need to scale up this curve. The VI characteristic curve in equation number 105.2 will scale up by a factor of 2. The open circuit power supply V naught and the blast resistor RB would need redesigning for the desired current to flow in the laser tube for optimum glow discharge conditions. So you see that these are over two equations, that is equation number 21 and equation number 22, that are required when, and these are provide the scaling laws for any gas laser. If we want to design any gas laser, we need to use these two equations. Pump rate and pump efficiency. We have the pump rate equation in the form given in equation number 23 obtained from slide number 106, and we have reproduced over here with the label of equation number 23. So Rp is equal to Nt times Ne multiplied by the average value of V times sigma, where N is the electron density, Nt is the total population present in the lower laser level, Rp is the pump rate, V is the velocity of electron, sigma is the ionization cross section. So where the electron density Ne is related to the current density capital J in the discharge through the following expression. So J is equal to E times V drift multiplied by Ne. This is the electron density expression written for the discharge in the tube. You see that Ne is present in both expressions, and we can eliminate the value of Ne, and then we obtain the following expression, that is Rp is equal to Nt times J into average value of V sigma divided by E into V drift, forming equation number 25. This is a more qualitative descriptor of a pump rate than the quantitative descriptor. The equation for the V drift from equation number 107.9 and TE from equation number 13 are reproduced here. So V drift is equal to, this is what we have already mentioned in equation number 9, and which is V drift is equal to sigma divided by 2 whole raised to power 1 over 4 and E zeta L over M whole raised to power half. And from equation number 13 we have TE is equal to 2 over sigma raised to power half and then E over 3K multiplied by zeta into L. So these are the two expressions that we have already obtained in equation number 9 and 13 respectively. From these two equations, it follows that V drift is proportional to the square root of TE. You see that if I take the square of both sides of equation number 26, on the left hand side I have the square of V drift, and on the right hand side I have E into zeta into L. And you see that E into zeta into L is also present in equation number 27. So I have V square drift proportional to TE, or I can write V drift proportional to square root of TE. If we assume a Maxwellian electron distribution, we find there that the average value of the average value of V times sigma is proportional to TE. So for this ratio, that is the absolute, that is the average value of V times sigma divided by V drift is now proportional to square root of TE, because the value of this one, that is the average value of V sigma, is proportional to TE. The value of V drift is proportional to the square root of T, and thus the ratio is proportional to the square root of TE. The gas pressure T and the tube radius R can be chosen to be. You see that for optimum value, we fix the value of P to be equal to P naught and R equal to R naught. That fixes the value of TE. So T is equal to T opt is equal to constant. Under this condition, since over T is constant, so we can say that the ratio, which is the average value of V times sigma divided by the drift velocity, this ratio is also equal to constant. So you see that when this is equal to constant, it means, so you see that this ratio is constant. It means that Rp is proportional to the current density J. So we have Rp proportional to the current density J. But from previous slide, that is from slide number 6, we can find that Rp is also proportional to eta P. So we have combined the two results. We can write that Rp is proportional to J times eta P. Eta P is defined as the ratio of the minimum pump power needed to achieve acquired pump rate and the input electrical pump power. Here we are talking about the pump power, that is the optical pump power, and here we are talking about the electrical pump power. So eta P is actually the ratio of the optical pump power to the electrical pump power. And the relationship of eta obtained from equation number 102, equation number 18 is given below. So eta P is equal to Rp multiplied by A cross sectional area of the tube, L length of the tube, L length of the active medium, H nu P, H nu MP divided by PPE, where nu MP is the frequency difference. Actually, this is the minimum of frequency, minimum pump frequency. So nu MP is the minimum pump frequency which is required to move the atom from the ground state to the upper laser level. So this is the minimum requirement of the frequency. Capital A is the cross-sectional area of the active medium, and L is the length of the active medium. Here, don't confuse L with the mean free path. Here in this formula, that is in equation number 28, L is actually the length of the active medium. So we have Rp proportional to J as mentioned earlier. And from here, from this, we can see that it is also obvious that the electrical pump power, that is the pump power given to the, that is the electrical power given to the pump PPE is also proportional to J current density within the tube. So these two quantities are proportional to J, and these have been highlighted in equation number 28 with red light, with red ink. So you can see that eta P is now independent of the value of J. Thus it follows that eta P is independent of J. An accurate expression for Rp would base on the electron energy distribution, which is quite different from the Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution must be modified to account all collisional processes, excitations, de-excitations of rotational, vibrational, and electronic levels, and to account all the species present in the gas mixture. The actual pump rate data requires computer simulation based sometimes on the unavailable data of the electron collisional cross section. So you see that sometimes we do not have the data of the electron collisional cross section, and we perform the simulation in the absence of this data also. In simulation, eta P may be assumed to be known. Thus, we can find out the value of Rp as Rp is equal to eta times P multiplied by PPE over A into L into H into nu MP. So this Rp is regarded as the pump rate equation and is often employed for calculations in laser physics based problems. So we can use this formula most frequently. Here we are assuming that eta P is known. So this is the end of slide number 107.